So at the end of class last time, I accidentally put a negative on that when I was helping somebody solve a problem. It should be positive when we do this. Part of the reason we picked these YLMs, or why we're using the YLM solutions, is because they were eigenfunctions of the L squared. They give us this constant value times the YLM again. The other one that we're going to use pretty regularly is the LZ hat, which on a YLM, let me make that a little bit more subscript M sub L. And we do M sub L here, just so we know it's not mass, it's not associated with spin, it's not associated with anything else we might look at. And then we also, oh, I missed something weird. And then we also know that the YLMs, these spherical harmonics, are an orthonormal basis set. If we're using the functions that are on the equation sheet, these are orthogonal and they are normalized. Now that's important because we're going to shift from talking, the thing we did Tuesday last week, and then we spent Thursday kind of working on solving some problems on a worksheet that was not recorded, sorry everyone on the internet. But Tuesday, we did the rigid rotor, or the particle on a sphere, three-dimensional object kind of like tumbling through space, but stuck at a specific distance. And there are some things that we can model like this, not a porphin ring, but there are things we can model like this. That's a side joke, sorry. There are some things that we can model like that, but it would be really nice if we had that variable distance as well. And that's where we start talking about hydrogen. So there's kind of two things that we add in at once to make this happen. One is we're going to add in that third dimension. We're going to add in that R dimension. So now when we write up our Hamiltonian, shifting, this is like important stuff from last time. Our new stuff, we're going to have a Hamiltonian. Right, when we want to start talking about hydrogen atom, again, I'm giving you the end of the story. There's some other things we have to do to get to this. We're going to have, this can go away, negative h bar squared over 2 electron, mass of electron, del squared for an electron, oh wait, before I get too far, hold on. So at this point, I got ahead of myself. At this point, like this is just kinetic energy, but this del is now not just going to be the theta and phi part, it's also going to contain a radial part. So that's going to be one of the new things that gets added in, is the fact that we're going to have, this del is going to have some radius parts to it as well. Radius is no longer going to be constant. The other thing we add in, which is what I just started writing and then erasing, so I was like, whoa, I wanted to say words. If we have an electron around a nucleus, it's going to be attracted to that nucleus through the Coulomb force. So there's going to be some potential energy interaction. So rather than just having kinetic energy, we're also going to have a potential part. Question?
Could you explain what that symbol is?
Oh yeah, so this is del squared. This is the Laplacian. I'll write it down here. We're about to write it down, but the long version, okay, I'll just write it now. Del squared for an electron. I'm going to need more space. Right, so del squared is pretty much like d by dx, d by dy, d by dz squared, d by dx squared, plus d by dy squared plus d by dz squared. It's a three-dimensional derivative function. So if we want to do this for spherical coordinate system, that del squared ends up being 1 over r squared times d by dr, r squared, d by dr, plus 1 over sine theta, d by d theta, sine theta, d by d theta, plus 1 over sine squared theta, d by d phi squared. That's what it is, right? So it's essentially second derivative in 3 dimensions, and because we've got that weird spherical volume element, we end up with these kind of sandwiched functions in between derivatives where we're going to have to use the product rule for derivatives in order to evaluate this. Now this looks scary. I kind of got sidetracked from telling you the end of the story here. This looks scary, but we can kind of notice that whole chunk is not L squared. L squared and eta squared are slightly different. This is essentially eta squared. Right? So this is some chunk, that's the angular part. If we don't have the h bars and stuff in there, we can relate this to L squared. This is different from L squared by just an h bar squared. So these two things relate to each other. Oh, by a negative h bar squared, sorry, there's a negative sign in there as well. But these two things relate to each other. The L squared operator and this look really similar to each other. If you remember Tuesday in class, we wrote them in terms of each other just to make it so I didn't have to write all of this over and over again. But here we can see that part again. You can also see, if you notice here, this is our LZ squared operator tucked inside there as well. So we've got our LZ component in there. We've got our rest of the spherical. So the rest of this would be like an LX, LY term, an LX squared plus an LY squared term. So that gets us all of that. And then over here at the end, we get this new radial piece at the end. So there's that radial portion at the end. Now that radial portion is not going to be all we worry about, because we're not just doing this for just a particle moving through three-dimensional space. We're going to do this for a particle attracted to the nucleus through the Coulomb force. Right? So we've got a proton in the middle, an electron being attracted to it. So we have some Coulomb potential. And we're going to have a non-zero potential here, whereas we're used to having a zero potential, but we end up with a non-zero potential. That non-zero potential is the charge of the nucleus, which is the number of protons times the charge of the proton, times the charge of an electron, divided by the permittivity of free space. That tells us something about how electric fields and electric attraction moves through space, with a 1 over r there. So we're going to have another piece kind of added into this to get the full radial portion. But we have this attractive force to it. Now, it's not going to be as scary as it looks because we're going to be able to use separation of variables again. And we're essentially going to say, hey, my wave function, if I wanted to look at a wave function for some r, theta, and phi, is going to be equal to something that solves this radial part with the attraction in there. That's going to have two values in terms of it, times our spherical harmonics we already solved to get the angular part. And so we can talk about this kind of radial portion and this angular portion, and we're going to be able to do some separation of variables. The n's and the l's and the l's and the m sub l's and the relationships of those all come out from doing the separation of variables, from treating the radial part separate from the angular part. That gets us that L that relates the two, and then separating out the theta and the phi, that gets us the m sub L. So we have to look at how that's all going to work. And again, guess how you would solve it if we wanted to solve it. Power series expansion. Right? It's another power series expansion that's going to get us another polynomial term. And so when we start looking at how we look at a solution to the hydrogen atom, right, just a nucleus with an electron, we end up with a polynomial times two polynomials. Right? So the function ends up looking kind of cumbersome. But the plots of it and the information we get from it and the way that we do operations on it, since we have these since they're eigenfunctions of these operators, turns out things work out pretty nicely. With this function, and so we can kind of do the same thing. We define our problem, we look at what it is, we get the coordinates and everything, we get some function, and then we can go ahead and say, if we have these size of n, l, and m sub l, we get energies associated with them. That's going to be negative z squared times e to the fourth mass of electron divided by 32 pi squared epsilon naught h bar squared times 1 over n squared. Turns out that there's not any dependence for this energy on L and m sub L yet. Question?
Is that ME or ML?
That's ME. Sorry, let me write that a little bit more clearly. Mass of electron.
Thank you.
Now, the funny part where you might... Oh, question, yes.
So the E, is that like the mathematical, like E to...
No, that's charge of electron.
Okay. So in both of them, it's the charge of the electron.
Charge of electron in all of this, yeah. Charge of electron. And to simplify things, it turns out this chunk, this whole, notice it's charge of electron times mass of electron divided by 32 pi squared, epsilon naught is a constant, h bar, everything here, this is all constants. And it turns out that this can be written in terms of the scientist who first kind of put this together, called the Rydberg constant. Do you all remember the Rydberg equation? Back 127, absorption emission spectroscopy, right? There was essentially an equation where we were like, don't worry about it. You never have to worry about it unless you're a chem major. Well, here we are, chem or biochem. So it turned out the way we wrote this in the past for those other classes is we wrote this as negative z squared RH over n squared, right? And that looks way more simple than this thing. That all comes out from figuring out what wave functions solve this differential equation with that radial part in there, and then taking those wave functions that are solutions to this, operating it on the Hamiltonian, and seeing what energies we get. And we get this nice 1 over n squared energy dependence come out, which tracks with what we see in hydrogen emission spectroscopy. Question?
Is this like an eigenfunction? Like, should there be a psi on the other side?
Oh, yeah. So, yeah, all of this times psi. Great. So, yeah, there should be a psi there. Thank you for that. Great. So it's an eigenfunction problem where this huge mess in the parentheses does become just the energy for the particle. So a little bit of spectroscopy is going to come up today, and this is how we get to it. But before we get to that, we got to kind of peel back some of the important things here. I want to write one more thing that kind of relates back to, I'm going to try to do a couple things that relate to our 127 past, 124 past question.
What's N again?
N is a counting number that comes out of this. This is like what we had in the particle in the box where we had like our N solutions. So from the boundary conditions of the problem, we end up with 3 quantum numbers when we do this. An N, an L, and an M sub L. The L and the M sub L are things that we've seen before. We've got this new quantum number N. And it turns out N is the only thing that affects the energy for this case when we've got the single electron system. One of the things that we're going to do is we're going to start to recognize that we can write down a psi 1, 0, 0. So that's an N equals 1, L equals 0, M sub L equals 0. And we might actually recognize that better that will be like a 1s orbital. Or we could have a psi 2, 0, 0. And that would be like our 2s orbital. 3, 0, 0 is a 3s orbital. We need to take linear combinations to get the p orbitals. We have to do some of the things we saw in the worksheet last time, where we have to take linear combinations of the +1s and -1s to get real functions. But these things are going to build into our orbitals. We're going to start building the orbitals to describe the electrons around a hydrogen atom. Then we'll start doing really weird things. Okay. So in this situation, we're going to have essentially 3 commuting operators that describe our system. We're going to have the Hamiltonian, where these things are going to be eigenfunctions of the Hamiltonian. And since we're using this same YLN part, they're also going to be eigenfunctions of L squared and LZ. So this is going to have, that's going to be our set of that's going to be our set of commuting operators. So we're going to be able to tell stuff about the energy, the magnitude of the angular momentum, and the z component of the angular momentum for these different objects. Now, there's a couple things that I ignored in how we get this set up. And I want to tell you about this. I'm going to do it relatively quickly. It's going to give some information about where the nucleus go. Like, I've got no nucleus information here. And it's also going to give some information about why are these N's, L's, and M sub L's related to each other. About that. Okay. So when we really stop, okay, before I get started, questions so far? So when we really want to start thinking about this, we should really draw a coordinate system where we've got a nucleus with like a plus z times the charge of an electron charge. And then we've got an electron. Let me draw this a little bit easier for me. Then we've got an electron kind of over here with charge minus e. Right? These two things are going to be related to each other on a coordinate system. We can imagine it in an, oh, why did I put x up there? We can imagine it in an xy coordinate system where there's some r vector to the nucleus, there's some r vector to the electron. So I'm putting a little arrow on top of these things to tell us that they're vectors. But it turns out the part that we're interested in is going to be this vector. That's going to be the distance between the nucleus and the electron. And as these two things move, as the electron moves and as the nucleus moves, it's going to be the difference of these two vectors that really gives us the relative distance of the two things. Now we can simplify this a couple ways. First off, this means the Hamiltonian, and this part you don't necessarily have to write down, but it means the Hamiltonian looks a lot more complicated than the one I wrote over there, if you can believe it. Our Hamiltonian would need to include that motion of the electron. It would need to include motion of the nucleus, which I just noticed I have a typo in my notes, but I fixed it on the board. So I put sub nuke there because it's the mass of the nucleus and the motion of the nucleus. And then we'd have some Coulomb force, Q1 times Q2 over 4 pi epsilon naught, 1 over the r nucleus vector minus the r electron vector, absolute value. And we can start to think about the overall energy associated with this thing. This is the part that I really like. If we think about the total energy of all of these interactions, we're going to end up, it turns out we can split the energy of interactions in different chunks. Some we've already seen and some that we have to explore now. So we're going to have this new, the total energy is going to be this new electrical component that we have with this new Coulomb potential in there. We're going to have some energy associated with vibration. We're going to have some energy associated with rotation. And we're going to have some energy associated with the nucleus. And it turns out this starts to get us to think a little bit more about spectroscopy. because each of these energy terms corresponds to a different part of the spectroscopic series. This is going to be our UV. Oh, that's not how you draw V. That electric component is going to give rise to our UV invisible spectrum phenomena. So if we want to understand UV invisible spectroscopy, we're mostly going to be looking at that part. Question?
What are the constants about the 4 pi E naught? Are those Q's?
Q1 times Q2, yes.
Okay.
This is the charge of the nucleus, charge of the, right, so when I plug this in, it's going to be Z times E for the charge of the nucleus, and then times E for the charge of the electron, and that's where you get the ZE times E, or ZE squared. We'll see that in just a moment. Question?
What's the subscript of
For this one? That's NUC for nucleus. So, and you notice in the part that we're going to get to, that thing is going to disappear a bit. Question here.
For the plus ZE, that's Z times E?
That's Z times E, yeah. Number of protons times the charge of the proton, where the charge of protons and electrons are same magnitude, just opposite sign. Yeah?
Does the arrow with the UV vis, does that mean like you can find the E elect from UV vis?
Both ways, right? We can find the E elect from the UV vis, or we can find the UV vis spectrum if we understand the E elect, the electronic part of the energy of the atom.
So by that extension, would E vibration be NMR?
Oh, not quite. E vibration is going to be our IR portion, infrared aspects. Which part's going to be NMR? What's the N in NMR stand for? Yeah, this one's going to be NMR. The rotation is going to be, let me make sure I get this right. The rotation is going to be microwave. The nucleus is going to be radio wave, which is going to be on the NMR scale. NMRs happen to work on radio waves, which is a huge problem if you're doing this in Riverside. What's that? I'm not perfect. NMR is the fact that it's on the radio wave scale is problematic if you're, say, in Riverside, where that's where I did my undergrad. I did undergraduate research in NMR, and it turns out that there's a really popular radio station with a really powerful broadcaster that's right next to the frequency for hydrogen. So we had these really nice, beautiful, we were up on the second floor, we had these nice, beautiful windows that we had to cover with aluminum foil, like thick aluminum foil. Because if we didn't, even with the aluminum foil, we'd still pick up this radio station, we'd see this really big spike. And it was just like, K-Earth, why are you doing this to me? Question?
Could you have asked them to change their frequency?
I don't know. We maybe could have, but then that probably not. They were around before we were. At UC Davis, we got around this problem. So I did NMR research in my graduate work as well. We got around this problem by putting all of our NMR instruments in the basement. So no windows. I spent all of the years of my grad school underground. It's great. It's great. So, but this gets us to start thinking. This is where the stuff we've been doing starts to have applications to chemistry, starts to have applications to research devices you have used and you are going to use. Right? Understanding UV and vis spectroscopy, IR spectroscopy, microwave spectroscopy, all of this, that all comes from understanding the quantum interactions of a nucleus and an electron to get started, and then how we build that up to more complicated systems. So, how do we simplify it? How do we complicate it? We want to get rid of, so the first thing that we do is we use this thing called the Born-Oppenheimer approximation. I don't have to tell people who Oppenheimer is this year. In the past, I have to go through a relatively long explanation of, physicist in charge of the nuclear bomb, did a bunch of physics before that, particularly dealing with nuclear motion, the motion of the nucleus, and quantum theory. And essentially what the Born-Oppenheimer approximation says right, the Born-Oppenheimer approximation essentially says the nuclear motion and there's two different ways we justify this. You can justify it just by the energy scale, right? Our electronic energies are the highest, largest part of the energy. These are also, I have these, happen to be in decreasing energy. So that electronic term is the highest energy term, if you couldn't tell by the fact that it was the UV vis. And then the nuclear energy, that's on the radio wave scale, that's going to be our lowest energy term. So there's an energy argument we can make for separating out these two things and saying, look, the microwave, even the rotational, the microwave, these are all going to be small additions to the electronic energy. They're still there. They're still important if we want to understand the microwave spectroscopy or the IR spectroscopy. We have to worry about that. But if we're just worried about the electronic spectroscopy, this higher energy, the UV vis, we can kind of ignore all these other terms because that electron is whizzing around the nucleus. The nucleus moves, but the electron just kind of responds before the nucleus can even do much. There's a couple popular analogies in the momentum space. The one that we use, it works at Cal Poly because we have a lot of cows here. Essentially, if you watch a cow walking around, there are flies whizzing around it. The flies keep moving so fast that it doesn't matter the cow is moving. Right? The cow's this large, massive nucleus, and the cow, the electrons are just attracted to it and keep, the flies, acting as the electrons are attracted to it and just keep swirling around it as it moves. And the flies don't care as it's moving. That's the kind of hand-wavy, cute picture you can have in your mind. Other examples of like traffic and stuff like that get too violent and scary, of like cars whizzing around a semi-truck and things like that. But the cow analogy works great. Now, this approximation is obviously problematic. We have a problem with it. Let's see, we'll do it like this. So we're going to have to deal with this at some point. Right? If you ignore nuclear motion, the motion of the nucleus, you're never going to have vibrational motion because that requires the nuclei moving relative to each other. And you're never going to have rotational motion because that requires the nuclei rotating around each other. We can talk about the electron rotating around the nucleus and that angular momentum of the electron, which is what we're going to talk about now. But eventually we'll have to build back in nuclear motion if we want to talk about vibrational and rotational spectroscopy. If we're just worrying about the electronic part, the electron's motion, the electron's behavior, we get to ignore this term, and we get to collapse this thing, the difference in these vectors, and just to get to the R1. So we get this down to our Hamiltonian is going to be equal to negative h bar squared over 2 mass of electron, del of the electron squared, minus plugging in what Q1 and Q2 are. That's going to be z e squared over 4 pi epsilon naught, 1 over r. Well, at this point, if we're doing it just as the difference, we can take off that vector point and just say it's a radial distance between those two. If we do it in r theta phi instead of x, y, z, we don't need that to be a vector anymore. So we get this nice term. We've already got what that del E squared part is, so we can get from this idea of nuclear motion the energies associated with the electron and the nucleus. and we can simplify using the Born-Oppenheimer approximation. Now, this energy argument and this kind of kinetic argument, this momentum argument of how fast the nucleus moves versus the electrons, they're a little bit of an oversimplification of the Born-Oppenheimer approximation, but they get us where we want to be right now in terms of simplifying our Hamiltonian so it's only one set of coordinates, right? If you think about this, I would have had to keep track of two sets of coordinates relative to each other, an r theta phi for the nucleus and an r theta phi for the electron. And that would have been like a lot to deal with. By using the Born-Oppenheimer approximation, we're essentially saying the nucleus is the fixed spot, and I'm just worrying about the electron swirling around it. Just doing a single electron for now. Okay. Once we plug all this stuff in, I'll do it over here. I'm going to erase some of my nice notes over here. Usually I don't like doing that, but I want to leave that stuff up for a moment. And I'm going to look at this part here. This is where we're going to talk in a little bit more detail about separation of variables. And I'm going to go ahead and throw on the last bit missing here. There should be, give myself a little bit more space, minus ze squared over 4 pi epsilon naught, 1 over r. So it's this whole first line minus this thing. The parenthesis does end at the end of that line. And now it's these two chunks together that make the radial part. And we can start looking at what happens as we do our separation of variables. The thing we can realize, this is a cute thing that I haven't mentioned before. I'm trying to figure out, I wish I had more colors. I need like purples and pinks right now. If this thing is Lx squared plus Ly squared plus Lz squared, and this is like our Lz component, it turns out this chunk, that would be like an Lx squared plus an Ly squared. And this is part of how we start doing our first separation of variables. So, our first separation of variables, keeping in mind we actually end up doing 3 separation of variables. Right, we've got this function that's going to depend on r, theta, and phi. And we split it once to give us an r part and a theta and phi part. But we actually solved this theta and phi part by splitting it up. I don't know if you remember this. People made fun of my capital theta, so I know I did it. But we have this capital theta part and this capital phi part that we're also doing a split for. So it's this separation of variables multiple times that gives us multiple numbers to keep track of what's going on. So for this first part, when we were splitting up our angular part, and I didn't do this explicitly last time when we did this, essentially we can say, hey, if I've got this Lx squared operator plus this Ly squared operator, and I just set it equal to some constant. Let's call it constant 1. If I wanted to have the Lz part add in and give us the function we have there, I can just go ahead and say my Lz operator is equal to negative constant 1. Now if I add these two things together, that constant disappears and I get the differential equation back. That constant that relates these two equations to each other, that's going to be m sub out. Splitting out that phi part from that theta part, using this, I'm just going to say they're both equal to some constant so I can treat them as separate things. But when I add them back together, I need that constant to disappear. So I have the constant be opposite signs. Question?
Is that ML or ME?
That's m sub out. Sorry, let me write that out. I got to be more careful with my writing now that we've got the m sub l's and the m sub e's. M sub l. The same thing happens, right? So now we can say, okay, well, let's look at this bigger idea. This whole thing is eta squared, so I can say eta squared operating, we don't usually call it L. Let's do it as L squared hat. I can also say, let me see how do I do this. I can also say my radial part is equal to some different constant. We'll call it constant 2. And then my angular part, my L hat squared, is going to be equal to that same constant, but a negative version of that constant. So now if I take that whole thing where there's a constant relating that part together to get this L squared, I can relate that whole chunk of the sines and thetas and phis to this radial portion, separating it out by saying, hey, if I add this radial part back to this L squared part, I want that constant to disappear. And this constant, I'll do it in orange again. The constant here is going to be related to L times L plus 1. And then the radial part by itself, is going to have some n values associated with it. And this gives us restrictions on how these things relate to each other, which are maybe familiar to us, maybe not familiar to us. Let's see, am I still on screen? Our n values can be 1, 2, 3, 4, all the way up to infinity. Keeps going, keeps going. Our L values are 0, 1, 2, 3, up to a maximum of n minus 1. So this n minus 1 restriction comes from this separation of variables in green here. The n value comes from just the radial part by itself, and then this restriction on the L values comes from the separation of variables here. Then our m sub L value also ends up with a restriction. We've seen this one before, plus or minus 1, plus or minus 2. Ooh, that's a weird one. Plus or minus 3, all the way up to a maximum of plus or minus L. And that restriction on the m sub L comes from this separation of variables between the Lx squared, Ly squared part and the Lz squared part. Now, some of this we've seen before, some of it we haven't seen before. We saw when we did the particle in a ring, m sub L had no restrictions, right? M sub L could be from 0 all the way up to plus or minus infinity. When we were doing the particle in a ring, we only had the phi part. There was no restriction. When we did the rigid rotor, the particle on a sphere last time, we ended up with this restriction. I didn't write it down like this, but this separation of variables we did to get the particle in a sphere solutions, or we borrowed to get the particle in the sphere solutions, that's where we now have restrictions on our m sub L value up to a maximum of L, plus or minus L. And now that we're bringing in this radial part, we get this new n value, we get this restriction on our L values, and we get this new n counting number. Oh, that's terrible. Usually I like to write down some of the m sub L. Okay, there we go. So I'll write down for fun, I'll write down what some of these R functions look like. But if you have your handouts from the first day of class, they're on there, right? The y, the spherical harmonics and these radial functions are all on the same page on different sides of each other. On the same page. I wish I had a camera operator. I feel like this could be so much better if I knew how to frame things. Right, so I'll just write a couple of these for fun. And make sure I'm not skipping anything here. Good. Okay. I think that's all this stuff. Okay. So, Born-Oppenheimer approximation, separation of variables, gives us this radial portion to solve separately from all of this angular portion. And we go through the same process of, hey, who wants to become a mathematician and solve an ordinary differential equation through power series expansion and then come back and do the rest of this class? And everyone's like, I'm trying to graduate, let's just get the answers from the mathematicians. And I'm like, okay, let's do that. So these solutions so we end up with functions, and again, this is a repeating function. So we have an R10 equal to 2 times z over a. I call it a naught to the 3/2 e. Now this is the exponential. E to the power of negative z over a 1 over r. Or z over a r. Ooh, what? No, say. Do not mess that up. It's not a 1 over r. It's z over a times r. I have it written down in my notes. Double check me. You should have that on your sheet as well. It should be e to the negative r or something, right? Okay, perfect. We'll get to what is going on there in just a moment. This is how you write it in the radial terms, just to start. R20 is equal to 1 over 2 square root 2 z over a naught to the 3/2 2 minus z over a naught r e to the minus z over a naught r. Now, as most of you noticed, you said, oh, it's rho, not r. If you look at the bottom of your table, there's a little explanation for how you rewrite r to rho. And it's this z over a naught thing that I have in there. It's like a 1/2 that. But these are the types of functions that we have. And guess what's nice about these functions? I'll tell you, this is a Hermitian operator. So these functions are going to be? They're eigenfunctions, and the eigenfunctions happen to be? And? Normalized, right? So this is going to make an orthonormal basis set. So our tricks that we started using last time when we were working on that worksheet are also going to come up. We can do integrals of like R10, R10 star. It's going to be equal to 1. We can do integrals of R10, R20, and it's going to be equal to 0. Right? We've got this nice orthonormal basis set that's going to make it so we don't have to do nearly as many integrals as we've done so far. Still do some integrals, but it's going to simplify situations. Question? Yeah?
Is it supposed to be z over a for the last term?
Oh. Yeah, so I do a naught or a. There's a definition for a naught. I'm trying to find it in my notes. I don't have it in my notes. A naught is called the Bohr radius. It's a combination of a lot of different constants. So that's a combination of a lot of different constants. We usually just say, I've got to know. So I have a worksheet for us to look at for the last 15 minutes of class. We might get to it a little bit early. But in this worksheet, I mentioned the, where did I put it? Planck's units. And in Planck's units, we said a bunch of things. H bar is equal to 1, mass of electron is equal to 1, charge of electron is equal to 1. And it turns out a lot of these things, A naught ends up being equal to 1 in those units. And it's really nice. Question up here and then over there, and we'll work our way around.
So are these R functions like also like the Y functions, and they're just like the way we separate out the radius?
Yeah. And it keeps going. Let me write one more for fun.
So then like the operators that would work on that would be like the Hamiltonian L squared and LZ?
Yeah. Now, L squared and LZ, since those are both angular parts, they're going to move right past it. Right? L squared and LZ actually don't operate on these because these have no angular part to them. But the Hamiltonian we'll operate on it. I want to write one more of these just to kind of show something, because this follows a lot of the same patterns that we've seen already. Let me see. Whoa, I do not see what that number is. 1 over the square root. Why do I have 243? That can't be right. Square root of something. Z over A naught. To the 3 halves. I've got 200, what looks like 243, and I know that, I don't think that's right. Maybe it is.
It's on the worksheet.
Is it 243? Whoa, it is 240, okay. It's 243. I haven't looked at R3 naught in a while. 6 minus 4 times Z over A naught R minus 2/3 Z over A naught R squared. E to the minus Z over A naught R. I'm missing little bits, aren't I? There's supposed to be a 2 in here.
Mm-hmm.
And is there a 3 in here? Let me see.
Yeah, there's an end term in the row.
There. No, there's not. Okay. Sorry. I've got weird marks in my paper that I wasn't sure if they were numbers or not. They're not supposed to be numbers. Those are that last term is always e to the minus a naught. It's always e to the negative rho over 2.
Isn't
Right.
there an n in there though for the row?
For which one?
For the row term, there's like an n times a.
Yeah. Oh, yeah. So there is supposed to be a 2 and a 3 for that n value. You're correct. Thank you. So the reason I wanted to write this third one is you can notice that it's just kind of, it's another polynomial series, and the polynomial series keeps growing and we can just keep going and going. Question up here?
With the definition of what A is on the worksheet, is the E squared the charge or the function?
Charge. Right, so, and that's part of why we rewrite things. Part of the reason we go to reduced mass is necessary for a lot of this, but there's places where we go to reduced mass, there's places where we go to, A, or what I call A naught, Bohr radius. Reduced mass is mass of an electron. It's to get away from that confusion of, are we talking about charge or are we talking about E, the what do you even call that, E? It's like inverse logarithm number, transcendental number. I should know what that's called.
Is it just Euler's number?
I think so.
Oh, it's Euler's number.
Euler's number. Yeah, thanks. Question up here.
For the subscripts of R3 is n, what's the 0?
So this is N and L. So this is the 1s, the 2s, and the 3s. If we want to relate this back to our general chemistry ideas. Question?
I got a little lost in the separation of variables part. So
Okay.
You're saying Lx squared plus Ly squared is a constant.
Yeah, it's not really a constant. But if I wanted to have this whole chunk, if I wanted to break up this whole chunk, I could be like, if this thing is equal to a negative constant, this thing's equal to a positive constant. If I add those two constants back together, it's like I did nothing, right? Because positive constant plus negative constant is like 0. So it's like I added nothing to this whole thing, and I just get this whole function back.
Okay.
So it's essentially, it's a trick, right? It's a trick to make it so we can talk about the thetas and phi's separate from each other.
Does it require that the Lx squared plus Ly squared equals the Lz squared?
Yeah, the same constant, same but opposite constant.
Is that always true? Like that those things are going to be equal to each other?
Equal with opposite sign.
Right, equal and opposite.
Right? And the reason that works is because if I add these things with opposite signs back to each other, that constant disappears, and I just get this whole thing back. Right? So if I take Lx squared plus Ly squared plus Lz squared, I get the whole thing adds up is equal to no extra term.
Yeah.
So it's this way to kind of just say, hey, I want to separate these two things out. I can multiply, I can just say there's some random constant, some counting constant that I need to keep track of so I can relate them back to each other. And now that counting constant that relates them back to each other has some restrictions on it because they do relate to each other. They're not completely separate. So it's a way where I can treat these variables separate, but still have a way that they relate to each other. Question?
Why is the 2/3 not squared?
Should the 2/3 be squared?
And then
I think it should be squared.
And then shouldn't it be plus that term, or no?
It should be. You're right. A couple typos. I'll have to double check my notes. So should that be squared? I'll have to check. I have to double check my notes and see where I looked this up. So there's a problem that I run into every once in a while that the textbook, the handouts are all in the notation of the textbook, and depending on which textbook you look at, you get slightly different notation between them. And I've tried to kind of do an in-between notation. I like it where you can see the radial term and understand that, because that's usually what we're asking about. This idea of rho is totally fine. It's just the radius times a bunch of constants. But I like to see the radius term. I like to see the radius term, because when we ask the questions that we're going to start asking, right, once we have these functions, so in terms of what we've done, right, once we have these relations of the quantum numbers, we've got our Hamiltonian with its crazy long del squared and its attractive force. We have a bunch of functions, these r's and these y's, that give us some solutions to it. We can start to ask interesting questions, right? So this is where we can start to ask questions. And the thing that we've always done, all of the setups of our problems have been define the problem, figure out what coordinate space we want to work in, what parameter space we want to work in, get some functions that solve the problem, either through our own mathematical prowess or borrowing other people's mathematical prowess, then start doing things like asking questions. What's the energy? More specifically, like what energies do we get out of it? What's our average radius? What's our average radius going to look like? We could ask what's the average angular momentum or specific angular momentums. We can ask for probabilities. Right, where again, we have to be careful. I hid something here, which I think we're all familiar with now. This d tau, if we're doing this in spherical coordinates, is going to be r squared sine theta dr d theta d phi. Right, it's actually going to be a triple integral in order to get our three-dimensional space, which I erased it, but this works out really nicely when we're talking about something that has that radial potential associated with it. It's really hard to rewrite these. Like, if you think this looks hard, if you tried to do this in x, y, z coordinates, it turns out that you can't use separation of variables, and it becomes really difficult to even try to solve the problem. Now, we can start to relate, once we have this nice work, we can relate back to like the LZs and the LXs and LYs. We can relate back to some of the things that we've done. But if we started with the XYZ coordinate system, things don't separate nicely. Because that 1 over r term would be like a 1 over square root of x squared plus y squared plus z squared. And how do you separate that? Like, it's got all three coordinates mixed into it in a square root of coordinate squared. So even though this looks like what the heck did you make us do, it's actually still the easier way to do it. Okay, now part of what becomes important here, there's a couple different things. Let me do one example real quick. Right, and I'm going to show you like how we would solve for an average R value associated with this, and I'm just going to do it for a simple function. I'm going to do it for the R10. I'm going to do it, I wrote it as R100. I'm going to erase these two. I'm just going to leave the 10 here for a moment. And I'm going to go ahead and ask one of these questions. What's the average R for a 1s orbital? That is to say, a psi 1, 0, 0, R, theta, phi. We know the definition, or hopefully we know the definition at this point. That's going to be the integral over all space for psi 1, 0, 0 star, R hat, psi 1, 0, 0, d tau. That's the simple version of it. And then we can start plugging in what all of these different things mean, where this is actually going to give us a triple integral for an R10 R part and a Y00 theta phi part. Oh, I did not give myself nearly enough space for that, did I? Rewriting it just down below here, sorry. If you wrote that down already, you're doing fine. I just need more space. Triple integral R10 R Y00 theta phi star times R times R10 R Y00 theta phi R squared sine theta dr d theta d phi. There's a d phi in there. You can see that, right? Still didn't give myself enough space. And I always like to put my limits on in the order I wrote my d's. So this would be from 0 to infinity. Theta is from 0 to pi. And phi is from 0 to 2 pi. Now, this looks pretty gnarly, but we can use some of the things that we know in order to simplify things. Notice I've got R pieces and I've got Y pieces, thetas and phis. So I'm going to go ahead and I'm going to split this into kind of two different sections. I'm going to have a double integral of Y00 theta phi star Y00 theta phi sine theta d theta d phi. Theta is first, so that's the 0 to pi. Phi is second, so that's the 0 to 2 pi. Times the integral of R10 R10 R R cubed dr, where the cubed comes from the squared times the R in there. Why is it nice to write it down this way? What do we know about the spherical harmonics? They're normalized, right? We're using these as already normalized, so this whole entire chunk just goes to 1. That's the beauty. Like, do we have to do that integral? We already know it's going to be equal to 1. So that whole thing is equal to 1, and then if we want to know the average radius, we just have to solve this last bit, which is the integral from 0 to infinity of R10. Also notice R10 is real, so I can just call this R10 squared R cubed dr. And now I've got a much simpler integral to start to approach. Orthonormal basis set is probably one of the best things in your life that you haven't heard of yet. Right? Saves us a lot of integral work. Question?
Where did you get the little r cubed from?
Okay, so we've got that r from two different spots.
Oh, okay.
We get it from the volume element, we got an r squared there, and since we're doing r average radius, that gets us r cubed. Now, if we wanted to do the same thing for radial probability, there's a problem in the textbook that asks about radial probability. You do need that r squared term when you're thinking about radial probability. If you're thinking about average radius, you end up with an r cubed. So at this point, we can write down like a 1s, a 2s, a 3s, a 4s pretty simply. The 2p is going to require some of that work we did last time where we're going to add the 1, 1, and the 1 minus 1 together in different ways to get rid of the imaginary part. So we can start to make all of our hydrogen-like wave functions, the 2p's, the 2px, the 2py, the 2pz. We can make d orbitals. We can start making all of our different hydrogen-like orbitals. And we'll start doing more of that in our next class, looking at it, looking at nice little energy diagrams like Chem 127. And then we'll say, okay, well, what are some of the consequences of having an electron around a nucleus? And there's kind of three weird things that we have to do, and this is what my brain has been frying about for the last week and a half. Because after we do this, term symbols, spectroscopy, and approximation methods. And we kind of they're all kind of like chicken and an egg, snake eating its own tail. We can't really do multi-electron systems without doing approximation methods, but you don't really need to do approximation methods to understand term symbols, but in order to do term symbols, you need to be looking at multi-electron systems. So it's just where do you start on this very scary merry-go-round? So we're going to look at that next time. I want to leave a little bit of time to start working and thinking about our coding activity for this week. 1 through 5, you saw my email, you looked at it. 1 through 5, the idea of a harmonic oscillator going through tunneling makes sense to you? I'm like a 2. It's such a weird idea to me. So we'll pick up with all this stuff next time. I might stop the video here and we're going to talk about the harmonic oscillator.